Our problem-solving technique this week involves making a systematic list. We'll start with this problem. At Gail's chocolate shop, there's $1 chocolates, $2 chocolates, $3 chocolates. How many different ways can you spend exactly $10 there? There's a number of ways of doing this, but what we're going to do is keep track of how many $3 chocolates we buy and then how many ways there are of completing the $10. So number of $3 chocolates and the number of ways. Now, what are our choices for the $3 chocolates? Well, to make $10 to spend $10, if we're buying $3 chocolates, we could either buy 3 of them, 2 of them, 1 of them, or none of them. So for each of these, we're going to figure out how many different ways we can spend $10. So if we make 3 $3 chocolates, well, obviously there's only one way. 0 2s and then 1 1. So this first column here is for the 2s, second column is for the 1s. So there's just one way, that's pretty obvious. Now, and we get 1 1 up here. Now what if we have 2 3s? Well, if we have 2 3s, again, let's keep track of how many 2s we use. 2 3s is $6, so we have $4 left to spend. Number of 2s, number of 1s. 2 $3 chocolates is $6. We have $4 left to spend, so we could either have 2 2s and no 1s, 1 2 and 2 1s, or no 2s and 4 1s. So these are all the ways we can do it if we start with 2 3s. There are 3 different ways. Now what about using just 1 3? Well, if we use just 1 3, then, so 1 3, oops, excuse me, 1 $3 chocolate. We need to get $7 more, and to do that using 2s and 1s, well, $7 more with 2s and 1s, we could have 3 2s, 2 2s, 1 2, or no 2s. And if we have 3 2s, then we'd have 1 1, 2 2s, we'd have 3 1s, 1 2, we'd have 5 1s, and no 2s, we'd have 7 1s. So this is all the ways. So this is number of 2s, that's not a 2 in that column. So this is all the ways if we use if we buy one $3 chocolate. So one $3 chocolate and 3 2s and 1 1 makes $10, or 2 2s and 3 1s makes $10, etc. So that's 4 ways. And finally, what if we have no 3s? So no 3s, and again, number of 2s, number of 1s, and then if we have no 3s, then we could have 5 2s and no 1s, 4 and 2, 3 and 4, 2 and 6, 1 and 8, or 0 and 10. So there's 6 ways to do it with no 3s. And so how many total ways are there to spend $10? Well, we simply add these up. 1, 3, 4 plus 6 equals 14. Total, make some more room. 1 plus 3 plus 6 plus, oops, do it in order. 1 plus 3 plus 4 plus 6 equals 14 ways of spending $10 on chocolate, which, by the way, is a very good way of spending $10, I think. Especially if I spell it correctly. Okay, so we kept careful track by the number of $3 chocolates we bought. 3s, 2s, 1 or 0 are choices for the $3 chocolates, and then we figured out how many ways we could do it from there. By the way, there's another way we could do this problem. I didn't do it this way in part because there wasn't room on my little slate here, but another way of doing it is with what's called a tree diagram, where we say, okay, we'll start here, and then the number of $3 chocolates we buy could be 3, 2, 1, or 0, and if we buy $3 chocolates, then we'll have 0 2s and 1 1. We have 2 $3 chocolates, then we could have 2 2s, 1 2, or 0 2s, and then this would be 0, 2, or 4 1s. So we have 3 different columns, one keeping track of the number of $3 chocolates, one keeping track of the number of $2 chocolates, and one keeping the track of the number of $1 chocolates. And we just continue this out and we'd see all 14 ways. In some ways this is actually preferable, but I would need more room in order to fit it here. And the other way we did it works too. So I hope this makes sense.